Postage.
Yikes.
So angry.
Okay.
You better watch Joanne now. If you got any good code
I know. You were one of the best around shirt is too short. Go back. And I was like, it's close.
Joanne, how do you use an inseam?
Yikes.
Awful.
Okay.
We're gonna start cracking down on Joanne.
Yeah.
What? For dress code violations. But there's any of them.
Send him to the office. Okay, so we're going to talk about two things today, which look somewhat intimidating, but they're both actually very easy.
How many is 7?
So you know the thing I said about having homework time? You're wasting it. So there are actually 6 sections in chapter 6, but we are only doing part of this one and none of the rest because we get into some really deep vector math and I didn't want to do it. So how's that for honest answers today? I did not want to do it, so we're not doing it. So this is the last bit that we're doing. This is the part of 6.4 that is easy. So the first thing I want to remind you is, like, when we do vector stuff, we can multiply vectors by a scalar. Remember, that just means a number. Multiply the x, multiply the y. We can add vectors, and we can subtract them by adding the opposite. So we add and we multiply vectors. Multiply vectors by a number. There's not really a way to straight up multiply vectors. We would never multiply the x's and multiply the y's together and call that a vector. But there is something called a dot product, which is a different type of operation. It's still an operation. If you were to say to me, how do you use it? I would say, read the rest of 6.4 and you will get the answer to that question. There are definitely applications to physics. But once you get beyond, like, work, you guys talk about work and force and things like that in physics, but I'm not good at physics, so that's why we're stopping. There are applications to this, but we're not talking about them. That's the honest answer. Okay, so on your pink paper down here, it says dot product. Okay, so if we got to define a couple vectors here because we're going to use both of them anyway. So this is a little bit of weird notation. It's just, we're going to talk about all these, and because we're talking, go ahead. Because we are talking about two vectors, we can't just write delta x and delta y because we got 2 of them. We've got a delta x and a delta y and a delta x and a delta y. So instead of delta x, delta y, we're just naming them something different. So to find the dot product, it looks like this. It looks like multiplication. So it's going to be a dot in between them like that. U dot v. So you would say u dot v. You don't say u times v because it's not straight multiplication. So the way that you do it is you do u1 times v1 plus u2 times v2. So it's weird because it's not just multiplication. You do multiply the x's and you do multiply the y's, but you add them together when you're done. So it's weird because you're taking 2 vectors, multiplying them with this dot product, and you get a number instead of another vector. So dot product gives a number, not an additional vector. But other than that, like, it's super easy to do. Weird, but not difficult. Okay, so let me show you a couple things. Give you an example. So let's say that vector u is 4, 5, and vector v is 6, 3. Okay, we're going to find u dot v. That is how you say it, u dot v. So u dot v is multiply the x's. So I'm going to write my work out this time for you because This is the first time we've done it, but I probably won't do it again. So multiply the x's. That's where the 4 and the 6 came from. Multiply the y's. 5 times 3. Add them together. If you need this, this would be like u1 and u2. This would be like v1, and v2. But I don't even think about that. I just go, multiply the x's, add them together, multiply the y's. So this is 24 plus 15. So the final answer would be 39. So it's weird because it returns you a number. Okay, applications to physics, like I said, but I don't know what they are. You can read the chapter if you want to read the chapter, which you don't. So I know that. So let's try. I want you to find the dot product if u is 0, 3, and v is 4, negative 2. Okay, please find u dot v. Okay, what do we got? Guesses? Yeah, negative 6. Okay, 0 times 4 plus 3 times negative 2. Well, that's 0 plus negative 6, which is negative 6. Okay, so let's do one more. Not much else I can do here. 2, negative 1, and v is 1, 2. And please find u dot v. Okay. What do you get? Yeah, you do get 0. So notice that you can have positive, you can have negative, you can have 0. It doesn't matter, but they are numbers. So this is 2 times 1 plus negative 1 times 2. That's 0. Questions on dot product? We're not getting into it any more than that. Okay, so the next thing we need to talk about is the definition of orthogonal. So this says orthogonality. That's just a property. Orthogonal is the definition. Orthogonal. So I was a little bit curious about that word. And I was like, I wonder where that word comes from. So what's the root word? Ortho. Where do we? Dentist. Orthodontist or
Straight.
orthopedic surgeon, right? Or you have doctors that are orthopedic doctors. So what do you think ortho is? Straight. Ortho is about straight. So I was like, oh, that's interesting. So orthogonal means that
Will we be drawing
nope.
for this?
Nope.
Thank God. We would not do it.
Okay. To vectors are orthogonal if they are perpendicular to each other. Okay, so you can kind of see why that would be straight because you're talking about 90-degree angles, like that's a perfect X. It's not slanted every which way. Here's the nice part. You don't even have to know anything super hard. If they are orthogonal, their dot product will equal 0. Must equal 0. That says must. I squeezed my S in there. So on your homework, like seriously, this is ridiculous, but on your homework it will say, hey, are these two vectors orthogonal? Find their dot product. If it's 0, they are. If it's not 0, they're not. So if you look up here, these two vectors in our example, these two are orthogonal because their dot product was 0. So let's see. R, just an example. U equals 2, -3, and V equals 6, 4. Are these orthogonal?
No.
That was a very fast to know.
Yeah.
Do the dot product. Yikes. Okay, so dot product 2 times 6 plus -3 times 4. Don't listen to Grayson because that adds up to 0. And so the answer to the question is yes. Okay. How about whoops, I don't want that. Let's go U equals 7, 3, and V is equal to 2, 5. -5, sorry.
No.
Still no. Because what's the dot product value? -1. So it's 14 plus -15, so it's -1. So not.
I told you it was no.
Right? So again, the only thing you have to remember is that if the dot product is 0, it means they are orthogonal, which just means that the two things are perpendicular. Now, the only other thing that you have to do with that is something like this.
Now we gotta find K. Yeah, no.
I'm serious.
Okay, so this is the other way that you will see this. You will have a vector, Javon. You will have a vector with a missing piece, and you have to make it orthogonal. So you're just finding the missing piece.
Oh, that's like an equation.
It is totally an equation, and it's like an algebra level equation. No.
No.
6 times 6 is 36, Javon.
Oh, wait a minute. It's negative 2. I thought I was adding something, not subtracting.
Yep. So
Bro, Charlotte.
So if you are doing this, you're finding the dot product. So 3 times 4 is 12 plus 6 times k. And what does it have to equal? It has to equal 0. It's literally going to end up being a 2-step linear equation. It has to equal 0 every time. Minus 12 divided by 6, -2. Yes. Yes.
18
So-
minutes, guys.
I know, it's a record. Bless you.
All year, bro.
Watch this. I'm not gonna get the homework done.
Why not?
Because that was just not actual. Just a couple. Wow.
So you'll get done with this. This will take you 10 minutes tops. Remember we talked yesterday about if the vector has an I and a J, that's just the two pieces in your vector, so don't freak out on that.
Well, because then,
It's on your side.
oh wait, that's true. If I get it done.
Hey, that's not the right page.
Yeah, it is.
442.
442.
What's up with your book?
What's up with your
I
book?
don't know.
What kind of book do you
That,
have?
wait, I got Garrett's book. That's why.
Why did Garrett's book?
Because Garrett likes to keep his stuff in my locker. I don't know why.
There's one back on my.
Do I have to show my work?
Under.
Is that
tried to bring his book.
Oh, it's up to you.
Nope.
Nope.
Up,
it's
on
literally
top.
right there.
Right by your hand.
Oh, right
Yep.
here.
There you go.
You told me like underneath the cabinet.
Underneath the papers on my cabinet. I did say under the cabinet.